In the last video, we referenced radiation units of measurement, and in this video, we will unpack units of measurement that you may encounter working in medical imaging. The purpose of this lecture is to review the one standard units of measurement referred to as conventional units and the more commonly recognized units of the International System or SI units. You should be familiar with both, since both are utilized in our field, and you should understand the relationship between the units. As with our last video, we will start with Rankine. Not the German physicist, but the unit of measurement. Rankine, abbreviated with a capital R, is simply the measurement of exposure to a surface, such as skin or an ionization chamber. It is the number of ionizations in the air, and that is really important to know to distinguish from other radiation measurements. The Rankine is a measurement of the intensity of the raw X-ray beam at a certain distance. It does not measure the biological effects of radiation. This is because the effects of radiation is related to how much energy of the radiation was absorbed by the body's tissue. However, there is a unit that takes into account for the amount of energy absorbed in the tissue. That unit is the rad, which stands for radiation absorbed dose, and it is abbreviated with a small r. The rad is defined as 100 ergs of energy per 1 gram of tissue. You need to understand the relationship between the Rankine and the rad. We will use the pelvis to demonstrate this relationship. The Rankine is the energy being projected at an object. Rads are used to calculate dose for X-ray exposures as well as those involving particulate radiation. In contrast, Rankines are only used in radiography. At 40 inches, this average pelvis will receive approximately 0.2 Rankines. This is the amount of exposure being directed at the pelvis. The rads, or radiation absorbed dose, is approximately 0.19 rad. It is slightly less than the Rankine measurement because some of the energy passed through the patient and is captured by the image receptor to create the X-ray image. However, 1 Rankine roughly equals 1 rad. There is only a slight difference between the two values. Technically, 1 rad equals about 0.96 rads. In general practice, the values are rounded and are essentially the same. The difference is a small amount of energy that did not get absorbed or attenuated. As a reminder, rads are used to calculate dose for X-ray exposures as well as those involving particulate radiation. Rankines are only used in X-ray applications. But the rad falls short in conveying the biological effects of radiation, and that is something we want to know, right? That's where the REM comes into play. The REM, or radiation equivalent in man or mammal, is a unit that takes into account for the type of radiation being directed at the subject. This is accomplished through a weighting factor. The more biological effective the radiation is, the higher the weighting factor applied. REM is determined by taking the absorbed dose, or rads, and multiplying by the appropriate weighting factor. We see that the weighting factor for X-rays, gamma rays, and electrons is 1. For beta particles, it's 1.7. Neutrons are approximately 10, and alpha particles have a weighting factor of 20. Let's look at a quick example. 1 Rankine of exposure will roughly cause 1 rad of absorbed energy, and an X-ray will cause 1 rem of biological harm because the weighting factor is 1. We can plug in some numbers to make our example more tangible. 40 Rankines would result in 40 rads, which would also result in 40 REMs for an exam involving X-rays. It would also be true of exams or situations involving gamma rays and electrons. However, we can compare that to alpha particulate radiation, where 1 Rankine of exposure will roughly cause 1 rad of absorbed energy and will result in 20 rem of biological harm because of the weighting factor of 20 for alpha particles. We can easily see that alpha radiation is more destructive and causes significant biological harm. But remember that we learned in our last video that alpha particles are large and are not able to penetrate deeply, causing damage only at the surface. So let's backtrack for a moment and take another look at the rad. If you recall, the rad is the unit for dose that tells us about the energy absorbed per gram, meaning a finite area of tissue. However, we typically are not imaging just a gram of tissue. We tend to image larger regions. In radiography, we may image an area that is 8 inches by 10 inches, or an area that is 14 inches by 17 inches. The 14 by 17 exposure is going to deliver more radiation to the patient because a larger portion of the patient is being exposed. To take into account for this larger area that is receiving dose, the dose area product, or DAP, takes into account for the collimated X-ray field by multiplying the dose times the field size. So in our previous example with the pelvis X-ray, the patient received 0.19 rad. The collimated field for the pelvis was 14 by 17 inches. Therefore, the DAP would be 0.19 rad times 238. This equals 45.2 rad square inches. DAP can also be written in centimeters if the field size was measured in centimeters. While Rankins is the unit of measure for X-ray exposure, Curies are used to measure the radioactivity or rate of decay of a substance. The Curie, abbreviated capital C lowercase I, measures the decays per second. It's the count of the decay events or emissions of energy from the radioactive object. 1 Curie is equal to about 37 billion events per second. Now that we have reviewed the conventional units of radiation measurement, we will review the SI units. SI units are part of the metric system. In the United States, SI units are becoming the standard for radiation measurements. As of 2017, the ARRT certification in radiography will primarily utilize SI units for questions involving radiation measurements. The first unit we will discuss is Coulomb per kilogram, abbreviated capital C / lowercase kg. This unit is the SI unit equivalent to the Rankine, but a conversion is needed. As with the Rankine, the Coulomb per kilogram measures exposure at the surface and can be defined as ionizations in air. 1 Rankine equals 2.58 times 10 to the -4th coulombs per kilogram. Dose is measured in gray, abbreviated capital G lowercase y. As with rads, grays measure the energy in tissue or the absorbed dose. 1 gray is defined as 1 joule of energy per kilogram of tissue. 1 gray equals 100 rads. Dose equivalent was measured in rems in the conventional unit system, but in SI units it is measured in sieverts, abbreviated capital S lowercase v. As with rem, the sievert gives information about potential biological harm. 1 sievert equals 100 rem. Becquerel is the quantity of radioactive material, not the radiation being emitted. It is the measurement of 1 decay event. 1 Curie is equal to 37 billion becquerel. Both conventional and SI units may be observed in medical radiation applications. Therefore, we need to be familiar with both unit systems. Exposure is measured in both Rankines and Coulomb per kilogram. It is the number of ionizations in air. Dose is measured in rads or grays and is the absorbed energy in tissue. While dose equivalent, a measurement of radiation harm to an organism, is measured in rem or sieverts. This is a biological unit, while the others are physical units. And lastly, radioactivity is measured in curies or becquerels. We also learned about the dose area product, or DAP, a means to take the field size into account to measure the potential overall effects of radiation to an organism. The DAP is usually represented in grays per centimeter squared or Rankines per inches or centimeter squared. Dose area product incorporates field size into its measurement to account for collimation or lack of it. I hope you found this video helpful to better understanding radiation units of measurement. In our next video, we will look at tools and devices that measure radiation.